about on chapter 8, the first couple sections. On chapter 8, comparing the equations for angular rotation, including theta for angle, omega for angular velocity, and alpha for angular acceleration, and a compared rotation of a girl and a boy on a merry-go-round as far as that's concerned. And again, comparing that back to centripetal acceleration from chapter 4, 5. And again, that's v squared over r, which we calculate as omega squared over times r, depending on what you're going. So that's section 1 and 2 of chapter 8. I'm now going to go on to skip section 8.3 in the text, and then talk about section 8.4, which directly relates to the lab 8, and section 8.4 is on torque. So I'll talk about that. I will then go into examples, section 8.5, talking about moment of inertia. And then finish up with angular momentum. Kinetic energy, 8.7, rotational kinetic energy, and then finally conservation of angular momentum. Okay, so what we're going to do, starting here, all right, again, this is part of the lab, is this concept of torque. All right, what does torque mean? All right, we know from earlier chapters, we have force. If we apply a force in newtons on an object, it will accelerate, given by mass times acceleration, will be the force, or if we're given the force and the mass, we can figure out how fast it'll accelerate by dividing the force by the mass. All right, torque, so this is all in one direction, all right? And we can either be positive or negative, depending on the direction we take. Torque, on the other hand, is rotational, and this depends on force and radius. And in this case, would be an example is if we want to apply a torque, we have a nut and we got a wrench we apply to it to make it turn. Now just trying to grab the nut and turn it is going to be very difficult. But as you know from experience, if you have a big wrench, the longer the wrench, and you apply a force to it, and the force perpendicular, you end up with a torque. So this is rotation. So we apply a force this way. We have a distance r from the center, which will be in meters, and it rotates like this. So it rotates counterclockwise. We're given the torque. The Greek letter tau is F times R when F and R are perpendicular. All right, they have to be perpendicular for it to be this way. You know from experience, you don't pull on a wrench by pushing on it. That's not going to do any good. You don't do it, push on it that way, it's not gonna make a turn. What you do is push it perpendicular. You wanna loosen it this way, you tighten it up going the other way. So this would be a positive torque, the other direction would be a negative torque. We're not worried too much about the signs in this case, but this is our definition of torque. Okay? So it's F times R, and the units are in Newton meters. Right, so that's torque. We can have other examples related to that. If it's at an angle, it would be given by the cosine, but we're not going to worry. I mean, it's a maximum here, it's net zero when it's in the same direction as R. So you want the torque to be perpendicular. So that's section 8.4 as far as that's concerned. Right? So I'll leave that up a minute, and then I'll go on to the next part here. And go from there. Okay. So I'm going to move on to section 8.5. I'll erase this for a moment and rewrite this. Okay, so we have, again from chapter, force is mass times acceleration, and we have force, well, let's leave it as we have. We have force and linear, rotational, we have torque, which is given time F times R. F times R, as long as F and R are perpendicular to each other, right? So now we have the next thing is mass, all right? So we have mass, linear, and we have Newton's second law of motion, F equals ma. All right, what's the equivalent for rotation? Well, the equivalent for rotation is the case of, all right, so comparing, we got mass, both these objects, this ring and this disc, weigh approximately 2 kilograms each, maybe 5 pounds each, all right? So they both have the same mass. But this ring has all the weight concentrated on the outside. This disc has all the weight distributed throughout it. So there's a difference between these two as far as rotational. Now on chapter 8, there's a link to a YouTube video of comparing what happens to the rotation of a disc and a ring rolling down a ramp. So I'll leave that to let you watch. I'll do another demonstration later on this. But what we have here is this concept of moment of inertia. And we use the letter I, and it's given by mr squared in for our general terms. So basically what this means, this is called moment of inertia. And it turns out how far the mass is away from the center depends on how easy or difficult it is to make it rotate. And this means, like for a ring, say this ring is 10 centimeters in radius and it weighs 1 kilogram, or 2 kilograms, let's say, 2 kilograms, then the moment of inertia would be 2 times how far? 0.1 squared, which would be 0.02 kilograms meters squared. So that's the units of moment of inertia. All right. So that's for when all the weight is distributed outside. Now what if we have something a little bit different? All right. If we have a disc, how do we do that? Well, all the weight is not distributed on the outside, it's distributed through the whole thing. So how do you compare that? Also, if you have this ring and made it bigger in 2 kilograms, this moment of inertia would be larger still because the mass would be the same, but R would be much bigger. So how do we compare these two? How we can do that is on your text in section 8.5 compares. I'm just going to show it for you, but what I'm going to do is with examples. Is depending on the shape of the object, the moment of inertia changes regardless of the overall radius of the object and the mass. So we'll compare 3 different objects here, and then I'll get to this last part. So if we have a ring like this, all right, then the moment of inertia, I, is mr squared, where r is the radius and m is the mass. If we have a disk or a solid cylinder, a solid disk, then I, make sure I get that right, is 1/2 mr squared. So this one, this disk would have a moment of inertia 1/2 of this, even though they both have the same radius and they both have the same mass of 2 kilograms. All right. And the final one will be a solid sphere, like a ball. So if you have a solid metal ball, then I is 2/5 mr squared. So that's what they would be. And the comparison in the video, if you look at that, if you notice, the more weight that's distributed outside, the harder it's going to be to turn it. And likewise, that case, if you want to keep it rotating a lot, you put a lot of weight on the outside. So like some type of ring where you want momentum, you do that. But if you have something where you want it to be able to turn easy, like a bicycle wheel, you try to put as little weight on the outside as possible. So if I was compared to 3, and you can see this, you would go from, for a given the moment of inertia is the same, as far, not the moment, the radius same, the mass, then the lowest one would go first, then the next one, then the next one, as far as that was concerned. And you can look at the video on the Chapter 8 links. It's a YouTube video, it's a couple minutes long, comparing those two. So these will be given to you if you need them for the chapter, or you can put those in your notes. Again, this is from section 8.5 as far as comparing those. So that's it as far as that's concerned. So what we would have then, so I'll leave that and compare one last thing here and then move on to the last part on conservation of angular momentum. So you can write these down. They're case there. Okay. So rotation. All right, linear, we have force. In rotational, we have tau is force times radius. For mass, we have The linear mass for here, we have I is mr squared. Rotational potential, moment of inertia, this is inertial mass. All right, then we have F equals ma. For Newton's second law, for here, we're going to have torque, not torque, but yeah, torque. So we have torque equivalent force, torque. This will be I times angular acceleration. So I is equivalent to mass, alpha is equivalent of acceleration. So these are equivalents for rotational. So you apply a torque to a moment of inertia, you can measure what the angular acceleration would be. And then finally, we have kinetic energy is 1/2 mv squared. Here, kinetic energy, I'll put in Ke, Ke is going to be 1/2 I omega squared. So exactly equivalent, but instead of mass, we have I, and instead of V, we have omega. So those are expressions there. As far as that's concerned, as far as units, torque is in Newton meters, I is in kilograms meters squared. Torque, again, this is Newton meters, and this is still in joules. So both of these are in units of joules for that case. So that's the part summarizing the comparison. You can look at calculate number problems. So these might hopefully give you some example of how to compare these numbers. All right. And finally, all right, I'll do the last section here on conservation of angular momentum. Again, this is section 8, last sections of chapter 8. I'll do one last one here. And so conservation of angular momentum. Now, if you remember from earlier chapters, chapter 6, we had conservation of linear momentum. But this is only true for collisions. So if I have an object with 2 kilograms moving at a velocity of 5 meters per second, all right, the momentum P is m times v, would be 2 times 5 or 10 kilogram meters per second. And it collides with a 1 kilogram object with velocity of 0, collides and sticks. Afterwards, you would have 2 plus 1 kilogram together. We'd have momentum before equals momentum after. So that would be 10 equals mass 2 plus 1 times what would be V final. So momentum afterwards, we would solve for that. V final would be 10 over 3 is 3.3 meters per second. So momentum before equals momentum afterwards in collision. Now again, we remember the energy lost in this kind of totally inelastic collision, but the momentum before equals the momentum afterwards. But we have to have some sort of collision for that to occur. We can do something similar, but we can do it with just one single demonstration without having a collision involved. So I'll leave that up for a second because that's part of what we have from chapter 6. So, okay. So I've got a little demonstration here. And I'll also use my little weights I got. What I have here is comparing. All right, what I'm going to have is I've got a rotating disc that I sit on, and as I rotate, right, I just move around. Now, what I'm going to do is have my arms stretched out. Let's move a little bit farther away so I don't hit the wall. Okay, that'll work. Okay, so I'm going to do this and then pull my arms in, pull them out. Notice how I pull them back in. Notice what happens when I extend them. I slow down. When I pull them back in, I speed up again. All right, this is conservation of angular momentum. When my arms are out, all right, I have mass, but the R is much larger, so my moment of inertia is higher. When I'm pulling it in, they're much closer, my moment of inertia is smaller. Now, how does this work? Well, the way this works then is that we have I before will be I, well, not I before. This term, angular momentum, right? So for linear momentum, P is m times v. For angular momentum, we use letter L, and it's I times omega. So I is equivalent to m, v is equivalent to omega. But we have angular momentum L. So if you have L before, so if I have my arms out, I is, say, large, right? And I pull them in, I is small. And I'm gonna just compare. But because I'm doing nothing to it, the momentum before, which is given by I large, and because my arms are much farther out, I'm rotating slower, so my omega will be smaller. Then afterwards, I push my arms in, and then I will be much smaller. And because of that, because these two will be equal, because I'm doing nothing else except internally, then omega will be larger. So omega, so omega small will be less than omega large. All right, so this is the case here, both cases. So this is how a figure skater, when she holds her arms out, spins slowly, pulls them in, spins much, much faster, as far as that's concerned. We also have other examples as far as, well, a perfect example is a comet. All right, a comet, which spends most of its time way out. All right, we just had the comet, whichever one that was. When it's out here, it's going, speed is slow because this distance, r, and its angular momentum, its moment of inertia, is very large. So to compensate for that, it will have a smaller omega. And when it comes by this moment of inertia becomes much smaller because the distance, the mass, this mass is much closer to the sun. This was much smaller, so it'll be going much, much faster. So we'll whip around. And this is the case of a comet then. So there's other examples where you can do this, see this, as far as that's concerned. So this is the concept of conservation of angular momentum.